So following on from the previous video, our aim here is to prove the mean value theorem. So our aim here is to get to this stage. So we are going to start from scratch and then slowly work our way towards this. This will be our aim here. Okay, so let's start from scratch here. So starting from scratch, the equation of a straight line and the equation of this straight line here will be given by y equals mx plus c. Now we know the gradient m here will be the gradient for the straight line will be the up and down here, which will be f of b minus f of a, okay, f of a, and then divided by the across here. The across here will be b minus a. So this bit here will be the gradient of this straight line here. So the equation of that straight line will be given by well the gradient so far will be this. Okay, so remember what for a straight line. Once you know the gradient, all you need to know is one particular point on that straight line. Well, we now know the gradient. Let's select one particular point. Let's select this point here. This point here will have coordinates a, f of a. So once with an equation for a straight line, once you know the gradient and you know one particular point, then you can come up with an equation for that straight line. So we know the gradient, which happens to be this. So it will be the equation for that straight line will be y take away the up and down of that particular point, which will be f of a, equals the gradient, which is this thing here. Let's just call it m for the time being, and then it will be x take away the across of that particular point, which will be a. So this here is your once you know the gradient of a straight line and one particular point, then this here will be your equation for that straight line. Okay, so far we know the gradient, and then we're going to select one particular point, this point here. So the equation for that straight line will be given by this. Okay, so that's the equation for that straight line. But we don't want to call it y equals f. We don't want to use y to prove the theorem, because we don't want to use y to represent the gradient of that straight line, because going back to the original theorem here is saying that y represents this complicated function here, this f of x here. So let's not use y. Let's give it a new name, g of x. Let's just give it a new name. Okay, so our equation for that straight line is given by this. Okay, but we don't want to use the y. Let's just call it g of x. Okay, basically here, add this block to both sides. That will then take you to here. Okay, and then but we don't want to call it y equals blah blah. We're going to give it a new name, g of x. Okay, because y has already been used. So the equation of that straight line will be given by this. Okay, and then so we know the equation for this straight line. Now we are going to define a new function where we are going to define a new function, h of x here. So we basically, okay, we're going to define a new function, h of x, but h of x is equal to f of x take away g of x. So basically what this h of x represent is, well, if you look at this, f of x, so let's just, f of x is right here. Take away g of x. Remember, g of x is the straight line. G of x is a straight line. So if you get f of x, take away g of x, then h of x represents this height here. Okay, let's look at a different point here. Let's look at this point here. So when you get f of x, take away g of x, then h represents this bit here. And then let's look at this point here. If you get f of x, take away g of x, then h represents this gap. The point here is that h of x, if you look at h of x, meaning the gap in between, you can see it's 0 here, and then it increases, and then it slowly decreases, and then the h of x, remember h of x represents the height in between. H of x is 0 here, and it's 0 here. Okay, so when you sketch a graph of h of x, when you sketch a graph of h of x, it will look like this. Okay, now we can apply Rolle's theorem. Okay, so whether we defined h of x to be this here, but f of x is pretty much stays the same. But we know the equation of this straight line here. We know g of x, so we can put our equation of a straight line. So this here is our equation of a straight line here. Okay. Remember g of x. Remember g of x is given by this. Okay. So this here is g of x here. We are going to put this into here. That will then take us to here. Okay. So now if you look at the graph of h of x, it will look something like this. There's going to be 0 here. It's going to be 0 here because let me just say it again. So h of x represents a gap in between. You can see that right here it's 0. Right here it's 0. So if you draw a graph of h of x, it will look like this. Now Rolle's theorem is that if you have f of a equals f of b, then somewhere in between the gradient must be 0. Even if it's something like this, somewhere in between there exists at least one point where the gradient will be 0. Okay, so because we know here f of a is 0 here, but basically h of x here is 0. H of x here is 0. So we know somewhere in between the gradient must be 0. So now looking at h of x here, we know somewhere the gradient will be 0. We are going to differentiate h of x. We are going to differentiate it because we know that the gradient will be 0 somewhere in between. So let's try and differentiate h of x. So this here is h of x equals blah blah here. Okay, we are now going to differentiate it with respect to x. You see, this here is just remember our graph here. This here, the coordinates here was a comma f of a. So you see, this f of a is just one particular point. When you differentiate it, it's a constant. Basically, it's a constant. When you differentiate it with respect to x, it will just disappear because it's a constant. So this is a constant. If you look at this b here is just a constant. B here is just an a here is just a constant. This is a constant. This is a constant. So when you differentiate h of x with respect to x, this will become well. Before you do that, visualize this complicated thing here as a number, as a block. So this is your block here, and then now you've got to get this times this. Don't forget a here is just a constant, and then this block times this block here, this complicated block. So we want to differentiate this here with respect to x. But bear in mind that this here is a constant. So visualize this thing here as one complicated block, and then this times this, and then this times this. That will then give you this. Okay? So now differentiate it with respect to x. So when you come to differentiate this later, this bit goes, because there's no x in there. Okay? So currently we are here. Okay, so bear with me. We are here now. Currently we are here. Now differentiate it with respect to x. So this will then become this. And then this is a constant here. It disappears. This is a constant. It disappears. So when you differentiate this with respect to x, you would just be left with this complicated block here. Okay. So hang on. So the gradient. So the derivative of h of x is given by this. So hang on. Let me just scroll back. So when you look at the function h of x, you know somewhere in between the gradient must be 0. So what you do is you look at your original h of x, differentiate that with respect to x. That will then give us this. So this represents a gradient of of h of x. Now you know somewhere in between h of x, you know somewhere in between the first derivative of h of x must be 0. Well, we started out with h of x. Differentiate it gave us f prime of h prime of x. We know somewhere in between there must exist a point C, somewhere in between A and B, where this will be 0. So looking at this here, we know that somewhere in between there must exist a C where this will be 0. So from here we're going to say there must exist a point C somewhere in between. So put C into here where the gradient will be 0. Okay, so that will then take you to this stage here, and then now you've got 0 equals this block, take away this block. So add this block to both sides, then that will then give you this. Okay, so this is now we've arrived at our destination. Okay.